Okay, so calculations. Woo. Okay, the idea of calculations is to work out the number of particles in a particular substance. So if I have 100 grams of water, I should be able to work out how many particles there are of that particular substance, right, of water, right? So to work out those things, we need to know a couple of things, right? So who's ever been to the bank and deposited coins?
Me.
Yeah? Did they count out the coins anymore? Someone goes 1, 2, 3, 4. They count in a little treadmill. So you pour it into the treadmill machine and it sucks up your things. How do you think it counts them?
Weight.
By weight and by size. Does that make sense? So it first of all sorts them out into sizes and then it sorts them out into weights. So let's just go imagine you had a whole bunch of 50-cent pieces, all right? So if you have a whole bunch of 50-cent pieces of maybe, let's say, 1.2 kilograms of it, right? But you don't know how many 50-cent pieces there are there. But let's just say that each 50-cent piece weighs 0.02 of a kilogram per piece, right? And this one is the total. Would we be able to work out how many 50-cent pieces there are in this sample? Yeah? How would we do it? How would we do it? The number of 50-cent pieces would be equal to what? 12, what, sorry? 1.2 over 0.02. Or if I was to put it into words, the total mass over the mass of, what would I say? One piece. Okay, one piece. Does that make sense? The total mass over the mass of one piece. Okay, and that would get me the total number of particles. Okay, so for all intents and purposes, to do these calculations, to work out how many of these particles there are, that's what we're working for towards, you need to know the total mass and you need to know the mass of one piece. Okay? Now, imagine Mr. Lim is an awesome inventor, and instead of counting out coins, I'm going to count out eggs. Eggs. All right? So, I'm counting out eggs. Because eggs are sold in a specific number, how many eggs do you buy in a carton? 12, which is also known as a dozen. You can buy half cartons of eggs and double cartons, I know, but yes, deal with it. We're dealing with dozens, okay? So because eggs are sold in dozens, right? If I had, like 40 kilos worth of eggs, and would it be useful for me to know how much each one egg weighs?
Yes.
Well, kind of, right? But because I want to sort them out into dozens, it's probably easier for me to know how much 1 dozen egg weighs. Okay? So that'd be, the 12 times the 0.6 kilograms. Yeah? So in terms of eggs, it's easier to work out the mass of a dozen eggs and then use that in that calculation. So I still have the total mass. 40 kilos. But now instead of using the mass per egg, I'm using the mass per dozen egg, right? So my formula will be instead of the number of 50-cent pieces, I'm going to be working out the number of dozen of eggs will be equal to the 40 divided by the 12 times 0.6, which is the amount which 1 dozen weighs. Okay? So that's the kind of idea that we're working towards. So in a calculation, finding out the total mass is kind of easy, right? Because you take a sample, you put it on a scale, you work out how much it weighs. Finding the total mass is easy. Finding the mass of each individual atom or each group of atoms is the harder part, okay? Luckily for you, it's been done for you already, okay? So what they did was, they said, okay, well, let's go work out how to work out a group of atoms, right? So if I say I have 100 hydrogen atoms, I have 100 helium atoms, and I have 100 carbon atoms. Are they all going to be the same mass?
No.
No, they're going to be the different masses. Why are they going to be different masses? Different numbers of protons and neutrons. Each of their nuclei is different. So 100 hydrogens might weigh X. Can we work out how much the 100 atoms of helium will weigh, roughly? Not 2x. You've got the right idea. Yeah? Liam?
Like X plus whatever
No, not that. It's going to be some multiple of. All right, so let's have a look. Hydrogen has a molar mass of 1, which means it has 1 proton. Helium has a relative atomic mass of 4, because it has how many protons, how many neutrons? 2 of each. So therefore, if I have 100 hydrogens, it's going to be X. 100 heliums will be 4X. Because it will be 4 times as heavy, because each helium atom is 4 times as heavy as a hydrogen atom. Make sense? Okay, so that means then 100 carbon atoms will be how many X? 12 times. Whoops. Okay, 12X. Right? Now, what they've done is that, okay, well, we know that there is a ratio between these. There's a common ratios between these things here. All right? If I was to say that, that's Y, we can say that that's 3Y. Yeah? Happy with that? But they haven't gone with the unit X for the hydrogen. Okay? In terms of relative atomic mass, remember, what is the thing that everything is relative to? What is the atomic mass unit? 1/12 of a carbon 12. So 1/12 of C12 is 1 AMU, which is what you do, and they compare all of these things to. All right? So instead of it being, that actually makes it right. 12x here is correct, right? Because it's 12 times the 12th of the carbon 12. Right? Making that 12x, this is roughly 1, this is roughly 4. Okay? So what they did was that they said, okay, well, if I got its relative atomic mass, 1.008, 4.003, right, and 12.01, right? If I took that relative atomic mass, these are all in ratio with each other, okay? Because that's still 3y if that's y, there, right? These are all in ratio with each other. So we can use the relative atomic mass. Then what they said is that, okay, well, let's just make this easy. Let's just say I have 1.08008 grams, 4.003 grams, or 12.01 grams of a substance. I should have the same number of atoms of each of those. Let's just go over that idea again. They're in ratio with each other because the nuclei are at different masses, right? Since they're in ratio with each other because they're of different masses, right? We can use the relative atomic mass, which is already in those ratios, and we can say that, okay, if I take that mass of a substance, then there will be the same number of atoms for each one. So 1.008 grams will be equal to X amount of atoms. This will be equal to how many atoms then? 4.003 grams of helium will be equal to how many atoms? X. They're all X. The same number of atoms will weigh different amounts. We said that before, the same number of atoms will weigh different amounts. So different weights can equal the same number of atoms, depending on what type of atom you've got. right? So therefore, what they did was that they said, okay, we don't know what this X value is. Let's go find out what it is. Okay? And so what they did is they did some experiments and rah. And they found out that this X value is 6.022 times 10 to the 23 atoms. Okay? Which is a lot. It's a super, super large number, right? And this number is known as Avogadro's number. Avogadro's number. Okay? With a capital because it's a dude. All right? So, Avogadro's number. That number is the number of atoms there are if you take an element and get out its mass, the mass of its relative atomic mass. All right? So, looking up at the periodic table, if I was to take a sample of nitrogen, I would need to weigh out 14.01 grams of it to get 6.022 times 10 to the 23. Any one of these elements, if I weigh out its stuff, so if I get 58.69 grams of nickel, I'll get 6.022 times 10 to the 23 atoms. Okay? And this number is effectively now our unit. Just like we measure eggs in dozens, we now measure everything within this number, and this number is called a mole. Right? That number is called a mole. Right? So, that leads us to a couple of ideas. Okay? Number one, the link between this and this is fairly straightforward when it's atoms. Okay? But if you want to go between, let's say, carbon dioxide instead of just carbon, I can work out the relative atomic mass of the carbon and the two oxygens. Yeah? Right? So it would be 12.01 plus 2 times 16.00. Where did I get the 16.00? Where did I get that from? Oxygen's molar mass or relative atomic mass. Okay? So that is equal to 44.01 AMU. And this is known as its relative formula mass. Okay? Because it's a formula of a substance. So the relative formula mass is effectively the sum of all of the relative atomic masses. Make sense? Yeah? The relative formula mass is the sum of all of the relative atomic masses. And sometimes you might see questions use the two terms at the same time. And you can also call it its molar mass, because it's effectively the mass of one mole. So molar mass, relative formula mass are the same thing, right? They have different units technically, but they are the same number. And then relative atomic mass is the kind of, you really should only use that word when you're dealing with atoms or elements individually, not any mixtures or compounds, right? So, we have to be able to work out the relative formula mass of various substances, okay? So, I'll pause this. Yes. Okay, so how do we work out the number of particles within those masses of stuff? So first of all, we need to work out the relative formula masses of each of these things here. So let's go work out the relative formula mass of O3. So I'll do it over here. Hello. Relative formula mass O3 is equal to, how am I going to work out the relative formula mass of O3? Actually, get out your data sheets now, because you need your data sheets now. Go, data sheets. Go, data sheets. Oh, actually, did you get a data sheet? You didn't get a data sheet. Have a data sheet. Right. Hey, look at that. Palm cards. That's what I like to see. Okay. Data sheet. Where's your data sheet? You suck. Yeah, that's right. I'm putting it on video. Yeah. Forever to be known that you suck. Lucky I haven't named you. Okay, so you'll get your data. Oh, you suck even more because you haven't brought yours either. Oh. Yeah, all right. Okay, so relative atomic mass of oxygen is what? Wait. Relative atomic mass of oxygen is 16. So I do 16, is that the relative formula mass? Times 3. Okay, which is 48. Is that right? That's 48. That's right. Oh. Okay, so that's 48 AMU. Okay. So that's the relative formula mass. So now so what I need to do now is I need to learn a new equation, which is this. Or actually a couple of new equations. Okay, so we can work out the number of moles of O3 from the information given. Okay, we need the mass and what's the molar mass as well, which is effectively the relative formula mass. Okay, so this is the new formula. N is equal to little m over big M, where N is equal to the number of moles, M is equal to the mass in grams, and big M is equal to the relative formula mass or molar mass, which are the exact same thing. Right? So, I have the mass, 14 grams. Okay? And I have the relative formula mass, 48. 14 over 48 is some value. .29. Okay? And this is 0.29 moles. Have a look here. Notice that I've got the unit here as MOL, not MOLE. That's the unit symbol for mole, for moles. I really shouldn't have put this grams in here either. Remember, this is all on video, so you don't have to really take too much notes because you're just going to be plowing through that worksheet in a moment. Right? So, 14 over 48, which is 0.29 moles. Now remember, 1 mole is equal to how many particles? What's that large number again? 6.022 times 10 to the 23. So, that's not what I want. The number of particles of O3 is equal to the number of moles times 6.022 times 10 to the 23, which is some value. 1.76 times 10 to the 23. Okay, I'm going to be going around to all of you to show you how to use the power button and to show you how to save numbers as well. Did I show you how to save numbers in your calculators before? Yeah? Okay, cool, excellent. Then I don't have to do that. Woohoo! All right, and this is particles or molecules for this one here. Okay? So that's how you do that one there. You work out the number of moles, and then you work out the number of particles. Let's do the next one, 56 grams of lithium nitrate. So what I would like you to do is work out the relative formula mass for lithium nitrate. Go. Use your data sheets. Find lithium, find nitrogen, find oxygen, and work out the relative formula mass of it. Okay. Okay. So, it is 68.951 grams per mole is the unit for molar mass. All right. Then I can then work out the number of moles of lithium nitrate by doing the 56, which is the total mass, over the 68.951. 56 divided by 60 by answer. 0.81 mole. And then I can work out the number of particles from that as 0.81 times 6.02 times 10 to the 10 to the 23. Which is 4.89 times 10 to the 23. Okay, particles. Okay. No, which part didn't you get? You have to ask now. How do I know what it is? Okay, where did I get the 68? So, you find lithium. Lithium was 6.941. Nitrogen was 14.01. And then oxygen is 16. But then you have to do 16 times 3. And then you add those three numbers up. And you'll get 68.951.
So you basically separate.
Yeah. Yeah. And then you just add them up. Okay, cool. More questions? Okay, what's the formula for nitrate? NO3, how many minus? 1 minus. Nitrate is 1 minus. You need to do more memorizing. Okay? So, that is... listening. So, with these last ones, we're happy with the idea that at some point you will be skilled enough to do these fairly quickly, get the formula of these ones, and then work out its relative formula mass, because it is just addition of stuff, yes? Finding and addition, all right? Then you use that and the mass to work out the number of moles of stuff, and then you can use it to work out the number of particles of stuff, all right? So if you look at this question number here, it's actually the same as the question over here, but without that extra step. So it's actually one less step. All right? So that's these ones here, but I'll go through a couple of those later on. Okay? But this one here is a little bit different. Okay? It's reliant on you to remember that the number of moles of something will be equal to the number of particles over Avogadro's number. Okay? So effectively, it's saying, okay, if I have if I was to replace this number here with 6.022 times 10 to the 23, I would have 1 mole of something. Right? Because it'd be the same number over the same number. It's 1 mole of something. Because remember, 1 mole equals that number of particles. So, in this case then, I would say, okay, not something, but I have cadmium metal, right? And I have 2.56 times 10 to the 25 particles of it. Okay? Then I would put that into the calculator. 2.56 e to the 25 divided by 6.022 e to the 23. And I would have 42.5 moles of this substance there. Right? But that's the moles. That's the number of moles, but not the mass. I need to work out the mass. So I need to be able to rearrange that equation from before, right? Where's that equation? Rearrange that equation here to work out the mass from the moles. How would I rearrange that equation there? N times which M? The big M. Okay, to solve for the number of the mass there, okay? So if I use that equation over here, okay? So I'm looking at working out the mass of cadmium is equal to the number of moles times its molar mass, okay? So 42.5 times the molar mass of cadmium, which happens to be 112.4, okay? 112.4, and that gets me 4,778.2 grams, okay? 4 tons of the stuff. No, 4 kilos of the stuff. All right, so that's how you would do that one there. You work out the number of moles by the following formula, where it's N of the substance is equal to the number of particles over Avogadro's number. And then you rearrange the other equation to get M of whatever, oops, is equal to N times M. Okay, and then you have to use, you have to get the big M via its formula again. Okay, so that's how you do that one, there. Okay, do you want me to go through one more? Or is that one still okay? Okay, then that one there, as I said, it's just the one before with one less step. And then this one here, the mass of the following substances. Again, this is just asking you to rearrange that equation. So the original form was N is equal to little m over big M. How would I rearrange this equation to get mass again? Again, it's just mass is equal to N times M. This is effectively the same thing as the one before, but without that extra step. So it's just this blue step here, because you're given the moles. Okay, so let's do one of those here. Number of moles of sodium ethanoate is equal to 1.8, which is the number of moles, times its molar mass, which happens to be 22.99 plus 12.01 plus 3 times 1.008 plus 12.01 plus 2 times 16, which is 82 and a bit. And then times that by 1.8, and it's 147.66 grams, because I'm looking for mass, not number of moles. Okay? So, that's the idea of the number of moles, the mass, and the number of particles. Okay? Again, try and do